evening, everyone, depending on where you are, and thank you for connecting to this session, which addresses a very hot topic, which is hydrogen and gas in the energy system. And so today we have 3 presentations that allow to address this topic from different standpoints. So we will start with a presentation from University of Franche-Comté by Vincent Bertrand on the impact of time-based modeling and the economic results tested on a gas turbine electricity generation case study. Then we will address a hydrogen scenario design by Gas Exporting Countries Forum with a presentation by Seyed, Mohsen, Razavi. And our third presentation addresses the economic evaluation of the system with electrolysis storage and a bus fleet case study from Germany. And the presentation will be given by Lukas Saars from Hochschule Niederrhein. So without further ado, I give the floor to our first presentation.
Excuse me, before we proceed, I just see that I cannot share the screen and maybe the host will need to let the presenter to share presentation. I am the second presentation, but I see this technical issue just now before proceeding.
You confirm it. You cannot share the screen right now.
Yes, I'm doing that now. It's just that my computer is a bit slow, so I'm really sorry for that. There you go. I think it should be good now.
Yeah, that's right. Thank you.
Yeah.
Good.
To be, yeah. Please let us know when you see the screen.
Yes, I can. Yes.
Okay. Okay. Okay, thank you. Good morning, everybody. Thank you for being here to this session. I just would like to give you some information before the beginning. First, as you see, I will not be the only presenter. I am with my colleague Alexandre Chailan from General Electric. So we will present the paper together this morning. And second, I just would like to say that what we present today is actually a preliminary version of a work that is still in progress. So we will just give you some first result and also some highlights for the next steps of the paper. This paper is about the way we can combine a gas power plant with hydrogen production and storage facilities in order to make them more profitable, compared with a situation in which each kind of device is run separately. So it's the question we investigate. First introduction. First of all, some contextual fact. To say that the development of renewable and especially variable renewable with the problem of intermittency and so on. So in this context, we need more storage and also some more dispatchable power generation unit in order to provide stability for the electricity grid, flexibility, backup facilities, and so on. And when we look at the paper that investigate the feasibility of power system with only renewables, we see that we always conserve some dispatchable units in order to provide flexibility. And in such a situation, it is very often gas power plants that burn renewable fuels, such as, for example, biogas, but also sometimes green hydrogen. So accordingly, hydrogen, of course, but also dispatchable units are expected to be part of future electricity system with high share of variable renewable in order to provide stability, flexibility, and so on. But the problem here is that when we consider these two kinds of technologies separately, Okay, so hydrogen production and storage on the one end, and on the other end, gas power plants that burn hydrogen. So separately, these two kinds of technology, in general, we observe that they are not competitive enough. So it is the starting point of our analysis, in which we analyze how we can combine these two kinds of devices in order to make them more competitive. And more precisely, we investigate the way we may generate additional product for the plant owner, in addition to the sales of electricity. For example, with hydrogen that is produced, this can be sold. Okay, this is an alternative, but we also want to consider something that is not integrated in the current version of the paper, which is about the way we may generate an increased quantity of flexibility services by combining the gas power plants with an electrolyzer. In order to illustrate this, if you want, it's like if you have two options that you can activate with the gas power plants and the electrolyzer, and compared with a situation with only one option that is only the gas power plant. If you want, with these two kinds of options, you may generate an increased quantity of flexibility service, and it is part of what we are going to include in the paper for the final version. Finally, we also investigate the effect of some price incentive. Okay, of course, carbon pricing, but also some representative subsidies, and especially for hydrogen. For the methodology, we use an LCOE and NPV approach, which is in principle very simple, okay, because it's a very simple approach. But in our case, we believe that this makes sense because this paper is a collaboration between University of Franche-Comté and General Electric, which is a company from the energy industries. And then in this context, such a very practical approach, we believe makes sense. And also this may be seen as a kind of first step in a more general research project that will lead to more extensive modeling approach. For the originality of our approach, it comes from the fact that we have implemented the calculation on an hourly basis with hourly data, and then this allows us to consider with more detail the opportunities that may arise from combining the two kinds of device. So that's the interest of our methodology. I give the floor to Alexandre.
Thank you, Vincent. Good morning to all. Yes, I'm going to present you the case study we've considered, and specifically the different scenario we've had a look at. So the first one on the left side of the corner, this is a baseline. We assume the gas turbine Picard power plant of 129 megawatts, running 200 hours a year, and fired with pure natural gas, in this case pure methane. The profile of the gas turbine is actually shown at the bottom of the screen in blue with the blue curve. And the business case, we make revenue by selling the electricity. So this is the baseline, and we compared all the other scenarios to this baseline. This is a choice we made. Then we have the baseline with external H2 co-firing. So why put some H2 for hydrogen? Why put some hydrogen inside the gas turbine? Well, obviously to reduce CO2 emissions. And so here we've assumed we mixed 30% hydrogen with natural gas, with methane. And in the second scenario, we actually buy the hydrogen from the outside. We buy it externally. And so then we've compared it to the baseline. And then for the scenario 3 and 4, the one on the right, we actually have assumed that we will produce the hydrogen directly on site, so collocated with the gas turbine power plant. And so in these cases, we have an electrolyzer, compressor, and storage system where we produce the hydrogen, and we produce actually hydrogen to be sent to the gas turbine. And we produce it by night when electrolyzer is plugged on the grid. And so in these two cases, the only difference is that in the third one, we only make revenue by selling electricity, while in the last one, we also allow to sell the additional hydrogen we can manufacture. And so the idea was to understand what were the break-even levels of those scenarios compared to the baseline. We've considered another few assumptions. So as mentioned by Vincent, we consider profiles. So in this case, profiles of natural gas, electricity from 2019 and from France. We have also assumed the constant price for hydrogen of 4.68 euro per kilogram, which is a range of price for green hydrogen, more or less. And as I mentioned, we have done the study relatively to the baseline scenario. And so one of the assumption set, we still have to, for scenarios 3 and 4, where we have the collocation of hydrogen production plants and the gas turbine power plant, we still have to size the hydrogen production equipment. And so we made a choice in this case, and we decided to size them for the gas turbine hydrogen needs. What does it mean? It means we're going to produce enough hydrogen so we ensure the gas turbine can run as per the profile shown in the previous slide. This is the choice we made. And so how did we do that? Basically, we fixed an electrolyzer size. And then by backward induction, we have calculated the required hydrogen storage capacity so we can fill the gas turbine needs. And this is what is shown on the curve here. The blue curve, you can see the combination of, on the y-axis, the storage size capacity in ton, and the x-axis, the electrolyzer size. So for example, with 20 megawatt of electrolyzer, we have somewhere around 60 ton or 55 ton of hydrogen storage tank required so we can fill the gas turbine needs. And then we also calculated the investment cost for both of them. So this is a red curve. So when we consider these combinations, what is the lowest investment cost combination we could get? So we precise it with a minimum cost on it, and the value we retain was the combination of 6 megawatt electrolyzer and 60.8 ton of storage. And so to this scenario and with this precising, we applied the time-based approach. Sorry. So what is the time-based approach? Well, usually when we consider and when we do LCOE and NPV calculation, we consider yearly averaged values for natural gas price, electricity price, and so on. So here what we did, as we mentioned, we have considered profiles for these values, so historic profiles. And how does it matter? Here is an example where we can see actually how it does matter. So if we consider the gas turbine covering 5% hydrogen, and the gas turbine being run only by day and turned off by night, and if we assumed we have high price of electricity by day and high price of natural gas by day as well, and a low price by night, just assuming this profile, we can see on the right-hand side table of the slide the difference we would get on LCOE and NPV value for when using conventional and time-based approach. And so if we take an example and look at the NPV, one can see that with the conventional approach, we would get a 27 million euro value at the end with the conventional approach, while a 78 million euro value with the time-based approach. What is the reason behind that? Well, you can see the contribution of each part, natural gas, CO2, hydrogen, electricity. Sometimes it varies depending on which approach we're considering. For example, for natural gas, we have minus 258 for the conventional approach and minus 280 million for the time-based approach. This is due to the fluctuation of the price of natural gas we have considered in this simplified example. So low price at night, high price at day. And we can see that at the end, it actually leads to a difference. And we have the same kind of results for the LCOE calculations. And we also see the impact from the electricity revenues that are different from one approach to another. And so what we see here on this table is that using the first approach, the conventional one, in our case, in this example, we have actually differences, and we have a misestimation of the natural gas cost on one side and on the electricity revenue on the other. And this misestimation, of course, it could actually lead to opposite decisions for the decision maker, because in one case you have, let's say, quite high revenue, 78 million euro NPV at the end of your lifetime, while in the other you have a way lower value. And so we believe the interest of the time-based approach is actually when you're going to have, high fluctuation in the prices, and this is especially what we're considering gas turbine Picard, which is making its business plan and its business case based on the electricity price, where we have high fluctuation of the price. And the way we see this approach is more as a what-if approach. What if last year we had some hydrogen on the plant? How would it have impacted the plant economics if we had, had some hydrogen on the plant? And this is more the way we try and see it. So based on this historic profile, how would the plant economics be impacted with such change or such other one? And so with this time-based approach, we applied it on the different scenario shown before. And here are the results. So it's quite dense. Basically, so as mentioned, we did the comparison of each of these scenarios versus the baseline. And so what you can see on each line, you have one scenario. So if we take the first one, baseline with external hydrogen co-firing, what we see in the first cell of the table is that we have an NPV value, which is of 10.7 million euro lower compared to the baseline. So this case makes an NPV 10 million lower than the baseline and gives an LCOE, which is 60% higher in this case again, than the baseline. And we have similar result for the two other scenarios. And we can see on the second part of the table, we have calculated the break-even prices and incentives required to make this case just as profitable as a baseline. And one can see that in the first case, a baseline with external hydrogen co-firing, we would need 10 million euro investment subsidy. So we're just as profitable as the baseline based on NPV calculation. And we can also see that we would need a hydrogen price as low as 0.74 euro per kilogram to reach the break-even, and a CO2 price as high as 624 euro per ton. And so now if you have a look at the global view of it, well, first we can see that all those cases, they appear to be less profitable than the baseline. And especially when we actually produce hydrogen directly on site with the hydrogen production plant. So we believe there are different reasons to that. And one of them is because we have sized the hydrogen production system directly on the gas turbine needs. We haven't considered any other use for hydrogen when sizing and doing the optimization on cost from the hydrogen equipment. And so in a second step, what we'd like to do is actually take this into consideration and we run the model with this. And the second thing we can see from the second part of the table regarding the incentives is that none of them is enough alone to, actually it's going to be hard with only one incentive to reach profitability on those cases, because the value we got from investment, from hydrogen price, and from CO2 price, they're actually still far from the market value that are currently in the market. Yeah, that's pretty much it. I will leave the conclusion for Vincent.
Thank you, Alexandre. Okay, for the conclusion, I would just remind the main result that Alexandre has presented. First, as we saw, the break-even values are far from the market value to be competitive, and especially if we consider the carbon price, we saw that it is by far higher compared with what we observe on the EU ETS. It's maybe explained, okay, by the fact that we consider each incentive alone, and as we saw, it is not enough to make a the system profitable. So an avenue to improving competitiveness, maybe to combine the price incentive, first of all, but also obviously to consider more products for the plant and the hydrogen production and storage facilities, such as we said, first of all, the value of flexibility services, and also maybe some other policy incentives. The other important result we saw come from the decision rules we have implemented for the equipment sizing of hydrogen. As we saw, this leads to high value for the LCOH, and then in turn it results in value for the LCOE and the NPV at the gas power plant level that are not competitive. And as explained by Alexandre, it is the consequence of the fact that the decision rules basically only relies on the gas power plant profile and on the hydrogen consumption that is needed for the gas power plant. So in order to improve that, an alternative would be to use other criteria for the decision rules, such as the fact of considering as an objective the fact of having a low value for the LCOH, sorry, which in turn will translate into more competitive value for LCOE and NPV at the gas power plant level. Very quickly, for the perspective, we may speak. We may discuss this in the discussion, but we want to consider the value of flexibility, as we said, and we have also some further research that are planned on this topic for the future of this research project. Okay.
Thank you very much.
Thank you for your attention.
Thank you very much, Alexandre and Vincent. It's a very interesting presentation. I think we have 5 minutes questions from the audience. I don't know if the session host gives the micro rights.
Well, yeah, there is a Mohsen. Sorry if I misspelled your name.
Yeah, Mohsen, yeah, thank you so much. And thank you so much for your nice presentation. I'm just interested to know a little more about the options that you consider to provide or supply the hydrogen. Did you consider a variety and different pathways to produce hydrogen in this levelized class, like for example, the blue hydrogen and electrolyzers, or the focus was mostly on the green hydrogen, I mean electrolyzers?
Yeah, so actually we produce the hydrogen in what we shown directly with electrolyzer system plus compression storage, and it was fed by the grid in our case. As French electricity mix is quite low carbon, we assume it was enough to have a low carbon hydrogen, but we could basically do the same with the model, considering electrolyzer powered by wind turbine, solar power panel, and so on. And we haven't investigated the other type of hydrogen, such as blue or gray hydrogen. We haven't.
And the price we consider is reflect green hydrogen is quite high. And
yeah, right. That's right. Thank you so much.
I don't see any other hands raised. So if you have other questions.
In this case, I have a question. So again, related to the hydrogen production, do you intend to consider time series for hydrogen production price? If I understand well your presentation, you have considered a fixed hydrogen price, and especially for the cases where you produce hydrogen on site, do you intend to consider the variation of hydrogen production costs depending on the electricity price, for instance, or something like such?
Yeah, we could actually. The reason why we haven't is because we couldn't find any value for that. So if we, yet there is not such a green hydrogen market to get hydrogen prices varying over time and such profiles. But obviously, if we have the values, same the model is ready to directly implement the profile in this case and try and study, what would be the best time to use this hydrogen, basically when the price is lower, and what would be the worst time not to use it when the price is higher.
Yeah, we focused on the electricity price because obviously it's the price on which fluctuation are more have a greater impact. And as Alexandre said, it's difficult to find data for the hydrogen price with such detail, but it's possible in principle.
And hopefully in 5-10 years from now, we could get some value and directly feed them to the model.
Perfect. Thank you very much. Thank you. Okay, so if we do not have further questions from the audience, I think we can have our next presentation.
Thank you.
And so I give the floor to Mohsen Razavi.
Thank you so much, Olfa. Thank you to all colleagues and friends that are here. So just let me to share my, so now I think I can share my presentation. So can you see my presentation widely?
Perfect.
Okay, good, thank you. Thank you. So thank you to all. Good morning, good afternoon to all of you, and thank you for being here in this session that is very interesting, at least for me, and I know for you. Hydrogen. My name is Seyed Mohsen Razavi. My first name is Mohsen, and I am from Gas Exporting Countries Forum. I've been working for more than 5 or 6 years here in Gas Exporting Countries Forum as Energy Technology Analyst. In our department, Energy Economics and Forecasting Department, we focus on providing the outlooks and forecasts for the future of the natural gas. And within these 2-3 years, as you see, the hydrogen debates are already expanding, and it's very important for the future of the entire energy system and has great impact on all other energy carriers, especially natural gas. So we focused on natural gas. I personally developed the hydrogen scenario for the first time 2 years ago, and last year I submitted this paper for the presentation in IAEE. Unfortunately, because of the COVID-19 and what you all know happened, so postponed to this year, but we revised it, and this year we are expanding this scenario to other scenario that I will introduce to you. So just let me go to the next slide. So I divided my presentation into 4 sessions, one slide about the GECF, and then introduction and basics, and a little about the technology status and updates, and at the end, hydrogen scenario. So as you see in this slide, Gas Exporting Countries Forum now is for 11 member countries and 8 observers, and as you can see here, more than 70% of the global proven reserves in natural gas are being controlled by the gas exporting countries, around 144 TCM. So in terms of the export, also more than half in both ways of the pipeline and LNG is the share of the gas exporting countries, 52% for the pipeline export and 51% for the LNG, and about the marketed gas production, also gas exporting countries have the share of 42%. I just move quickly on why we focused on the natural gas. So the carbon neutrality and the debates around the carbon neutrality is now very important, and we see that, and we actually trust that the board and also energy societies will go to the carbon neutrality. Only last year, you see that a lot of announcements, a lot of strategies announced regarding to achieving the carbon neutrality, even for example, to China that is by 2060, but most of other countries have the ambitious plans to have carbon neutrality by 2050. But what is the carbon neutrality? There are a lot of aspects, and all of us know that there is no single and sole solution to the carbon neutrality. So policy and regulations, optimizations between the balance supply and demand, and managing that balancing, and also energy conservation and energy efficiency enhancement. All of these are the aspects of the carbon neutrality. But providing the clean energy is a very important aspect of the carbon neutrality. And providing this clean energy, as you see, as I see, and based on the opinion of the GECF, three main parts are being to participate and cooperate to the carbon neutrality, and these three fundamental issues are not inevitable. Natural gas with CCUS, renewables, and hydrogen, that is fuel based by these two other sector. So if we take natural gas with CCUS to provide hydrogen, we have the blue hydrogen, and for the renewable, we have the green hydrogen. So I just moved to the modeling, and so I just introduced that we have a very sophisticated model here in GECF, and all the colleagues are working with that, and it's very sophisticated and very wide. And so you see the architecture of the model here. We have, for example, in the demand part, we have time series microeconomics data, that, and also in supply and trade part, we have the linear programming, or to be more exact, mixed integer programming. So within this model always, and actually it's 5 years that we have been publishing. Now, the only outlook focused on natural gas, that is global gas, GECF global gas outlook. And this hydrogen scenario will be a part of the global gas outlook this year. However, we developed it 2 years ago, but we try to develop to one point and then publish within the global gas outlook. But last year we published as a byproduct of the global gas outlook. So I go forward and just introduce to you that in GGM, we don't focus only on natural gas. We see a lot of sectors, like, for example, in final industry, domestic sector, transport, in all parts, and also in power, refinery, and some other energy sectors. Also, we have 35 different fuels in our model that, as you can see, one of them is hydrogen. We added hydrogen to that model around 3 years ago, because we found that the hydrogen will be an inevitable part of the energy in the future. We even like an intermediate fuel or a final fuel. So let's go to how we develop our scenarios. You know, in GECF, in technology part, I personally worked on a reference technology map that all studies on technology, on any part of the technology, will fall in one or some of these boxes that you see in this diagram. So we have different levels of the energy carriers in the entire energy system. We have the resources and the final energy consumers. And in a hydrogen scenario, so these highlighted boxes that you see are the main points that we need to touch. So just go through the how and what type of the hydrogen we touched in our scenario. As you see, there are different pathways to produce hydrogen. So I just provide a simplified chart in the spectrum of the hydrogen, that you can see how gray hydrogen has been produced so far, around 80 million ton dedicated hydrogen, and more than 105 million ton of the hydrogen totally. So if we applied a CCUS to what we have now, like based on the natural gas or coal, so we have the blue hydrogen, and if we produce the hydrogen through electrolyzers with the power supplied by the renewables, it is green hydrogen, and in case that is from the nuclear power plant, it's yellow hydrogen. Another very important technology that we see will have a very significant share maybe in the future is turquoise hydrogen that is due to one technology that pyrolysis that is not very mature now, and unlike the other technologies that now completely can say that they are mature. So it gives us hydrogen plus the solid carbon that is even very valuable. And even now, if we have pyrolysis in some parts, it's because of the carbon, because of the marketing carbon. But in the future, maybe both of these two materials can be traded, for sure hydrogen and also the carbon. That is very important. So we have in production of the hydrogen, we need to consider that we have to look into different categories, raw materials and energy needed. So sometimes we use the fossil fuels as the raw material, and again we need fossil fuels some for the energy needed. I will elaborate a little more when I am presenting some on the hydrogen. So let's go to the technology status like now. So steam methane reforming, you know that it's a very common technology for producing the hydrogen through natural gas, reforming natural gas. But I brought this slide here intentionally to say that even if in blue hydrogen that we say that CO2 is being captured before the combustion, that is a pre-combustion carbon capturing, but still within most of this process, we need some fuel to provide heat for the process. And the fuel that we use to provide that heat, that you say that the CO2 from that part is mostly remains unabated through even the blue hydrogen. So another thing that we raise in our scenario is that even if we want to go for the carbon neutrality, maybe blue hydrogen alone is not enough in case that we just capture the carbon through the steam methane reforming. We need and pre-combustion. We need to capture carbon even post-combustion in that place that we use the fuel for the heat. Or maybe we need to apply or employ some other technologies like renewable here. So a cooperation between renewable and natural gas here can be a very good solution to this idea. So even we have the autothermal reforming and also the pyrolysis that I talked very simply, and here you can see the chart. So I go to the last part of this presentation, that is how we see and the result of the hydrogen scenario. So we considered in all of these sectors that you see employment and usage of the hydrogen, not only through the pure hydrogen, but also in medium term and short term, as the other colleagues that worked on that in the power sector. We have this idea to mix hydrogen with natural gas and use again in very common and conventional technologies like power plant, that we saw that very nice power presentation from the colleagues. So even we consider this in the medium term to mix the hydrogen with natural gas, and you know that even just very recently, previously most analysts thought that maybe up to 20% is fine and without very huge adjustment and changes in the technology. But now we see that maybe with more share of the hydrogen in the mix, we can derive most of the current and conventional technologies. So we considered in the medium term, but in the long term, we know the energy system needs the pure hydrogen. So we considered pure hydrogen for some other sectors like transportation. That is a very, some of very important hard to abate sectors are falling within the transportation, you know, like marine sector, like aviation, like heavy long haul transportation. So transportation will have a very good and very huge potential in absorbing the hydrogen in the future, and also in the industry in high grade temperature. So we see that electrification is challenged, and so like other hard to abate sectors, in this sector, in some industry sectors, we need pure hydrogen in the future. So I just provide for you some of the intermediate results, and as can see some as from another angle, we can say that they are assumption, but we see, for example, we considered for the building sector, even in commercial and residential, more than 4% of the all energy need for heating to be provided by hydrogen by 2050, and even some fuel cell power plant in the future. We say that, as you see in the right chart, more than 35 gigawatt of the fuel cell power plant we consider to be online on by 2050. In transport sector, for example, in passenger vehicles at right chart, you see that more than 70 million vehicles we assumed to be using in the future by 2050, compared with around 15 million ton in the reference case scenario. And also in light commercial vehicles, also you see more than 12 million vehicles we say. In two very important industry, iron and steel sector and also chemical sector, we say we may have this 10% and 8% of the all heat needed by 2050. I just need to mention that. So we consider this scenario started last year, I think, beginning of the 2020 or maybe end 2019. And at that time, so we had our assumptions a little conservative. But now, for this year that I will tell you how we want to develop our scenario, we say more, even more than this assumption, potential for the hydrogen to penetrate. I just go to the result of this final result of the presentation. You see that even in sorry, I need to bring this one. Okay, so on the left side, you see the pie charts showing the hydrogen the share of the sectors in different scenarios, and also in 2019 for hydrogen. You see currently, or in 2019, more than 50% of the hydrogen produced is being used in industry for as feedstocks, not as energy. And also 33% in refinery for the cracking sector, and so it's still a feedstock. So more than 80% of the hydrogen is not feedstock. So feedstock is the most way that we use hydrogen now. But by 2050, in both base case scenario and also in hydrogen scenario, you see that in hydrogen scenario, more than 33% of the hydrogen will be more than 33% of the total hydrogen produced by 2050 will be in transport. That, as I presented, mostly in heavy line haul transport, in marine sector, in train, some in aviation, like for when we produce biofuels using hydrogen. And on the right side, you see that the total production of the hydrogen is forecasted to be around 500 million tons of hydrogen by 2050, 475. So even, for example, recently, IAEA also published its net zero scenario. And in that scenario, the forecast for the hydrogen is 520, if I'm not mistaken. Even the Hydrogen Council also see around 530 for the hydrogen, million ton of the hydrogen by 2050. Next slide will show the source of the hydrogen. So you see currently in 2019, mostly hydrogen, even more than 98% of the hydrogen is produced through reforming fossil fuels, even coal, oil, natural gas, without any carbon capturing. So for now, 60% is based on natural gas without carbon capturing, that is gray hydrogen. But in 2015, based on the scenario that we developed, still we see that most of these technologies will be applied, will apply the carbon capture and storages. And you see for the total hydrogen production by 2050, more than half is from the blue hydrogen and based on the natural gas. So we believe that natural gas will take a great role and will keep its role, but in a decarbonized way, to be exact, in a decarbonized way through the blue hydrogen and participate more than 52% to the total hydrogen production that previously I presented, that is around 500 million tons. So my last slide is regarding to the carbon saving of this scenario. That can be much more than this, even in the new update of the scenario that I will tell you at the end. You see that based on this is the difference between the base case scenario 2020 and the hydrogen scenario 2020. I also showed in the spot what we had in base case scenario 2019. So you see that only with applying this not very aggressive, maybe conservative penetration of the hydrogen into the energy systems, we may have annually 3.5 gigaton of the CO2. That is totally more than 60 gigaton by now, from now by 2050. Only with this very moderated penetration that we consider. So for the next step, I just need to go to my first slide here. For next revision, we divide our scenario into two scenarios, carbon neutrality scenario and blue hydrogen scenario. And in carbon neutrality scenario, we consider some other efforts in carbon neutrality. And for the blue hydrogen, we consider how blue hydrogen can participate to its maximum potential. Thank you, back to you.
Thank you very much for this very interesting presentation. I think, again, so we have 5 minutes questions from the audience.
So for now, I don't see any raised hand. But,
yeah, Alexandre and Vincent.
Oh, okay, that's a
that was real
hand. Yeah,
hand.
that was a real virtual hand.
Yeah.
Okay, first, thank you for this presentation. That was very interesting. First, I have a question to understand the perimeter of the study. Is that worldwide or only the GECF countries? And a second question that is related to the first. You mentioned at the beginning of the presentation the gasification around coal power. Okay. And I wonder if you plan to consider the European coal phasing out plan in this case, because we know that there is some plan to use a conversion of coal plants with biomass, for example, but maybe also with hydrogen in order to comply with the coal phasing out plans. Sorry. So did you have a plan to consider it in your analysis?
Thank you so much. I got your second question, but first question, can you just ask it again? I didn't get it.
The perimeter of the study, is that worldwide or not?
Right. You know, yeah. As just let me to share this slide again with you, and yeah. You see the slides, right? Yeah. You see, yes. You know, we implement in terms of the method of our study and scenario. It is within the framework of the global gas model, and by implementing that sophisticated tool, global gas model, and within the framework of global gas absolute. So yes, so we this is very wide. You know, it's a lot of EVUs formulation and model in EVUs working with another optimization solver that, as I told you, mixed integer programming. So previously we applied a Microsoft Solver Foundation. Now Garubi is being applied, and with some other calculations that are being fed to the model. So the model itself very huge, and as you said, it's very wide, and it's the original and the main model that the global gas outlook is extracted from. And then we first produce our reference case scenario for the global gas outlook, and then we apply our changes, like for example, changing parameters in any parameters in linear and also in time series macroeconomics model to develop our scenario. For example, in hydrogen scenario, what we applied in this revision, some enhancement and usage of the hydrogen in sectors, and some potentials that we let model to go through, and some, for example, like development of the pipelines and access to the hydrogen for some area of the world. In this case, we develop the scenario and then run. So iteratively, they run together. So the marginal cost of supply will be fed into again the demand part and demand also. So that's right. That iteration will go to the desirable convergence achieved. So this is about the methodology that we apply in GGO, that this hydrogen scenario is part of that. And regarding the coal and the gasification of the coal, so that's, you're right. You know, even coal now has a part of this slide. You know, for example, now we see that coal, 27% of the current hydrogen production is based on the coal regasification, 27%. We consider some advancement in this, but based on the policies that announced and based on some other applications and forecasts that we had around the coal and policies, the results will be on 9%. So nothing is excluded in the hydrogen scenario, and in all of our scenario, even the carbon neutrality, they are included. But the situation is how that in terms of the cost and in some other prospects, they cannot gain a significant share. But we don't forget that, for example, the only complete supply chain of the hydrogen now project that is in Latrobe Valley in Australia is gasification of the coal. So, you know, coal cannot be omitted completely for the production of the hydrogen. Even now in Australia, in Latrobe Valley, they're working on that, and this is a complete supply chain of the natural gas, because the hydrogen, supply chain of the hydrogen, because that hydrogen produced from the coal implementing the CCUS, that is again a kind of blue hydrogen, gonna be liquefied and be shipped through the marine route to Japan and being exported. So this is the first project in terms of the exporting hydrogen with the hydrogen, I mean through the liquefied hydrogen. We had another export from Saudi Arabia to Japan last year that it was ammonia, but so we need to consider that carbon is still there, but coal is still there, but maybe we not share that now currently achieved. Back to you. Yeah, back to the moderator.
Alex, okay. Thank you very much. I have a last question for you. Yes. So in the model, do you have a vision country by country, or is it like a global model?
No.
And
yeah.
so if you have a vision by country, I see in this specific slide, so thank you for leaving it.
Yeah, unfortunately, yeah, I didn't. Yeah, I didn't bring that geographical situation of the model into the slides, and you are completely right. Yeah, we see country by country, actually more than 144 countries we have in our model. Some aggregations, only some aggregations in Africa we had, for example, so like, for example, Eastern Africa or such a things that is not completely by country level. But in all other places, in all other continents, we have country by country. So we even for the imposing the assumption, I need to impose the assumption to different countries. But in some cases, for example, I choose one group of the countries, for example, OECD, Europe, and so for them, consider one similar, for example, assumption into that. But still, there is ability to go through one by one. And another advancement that we think for this year, because last year we had a lot of definite hydrogen strategy announced by the country. So for this year, we may apply and impose those definite strategies of the hydrogen into the model, because we have the ability to do, but previously it was not very huge amount of the hydrogen strategy announced, but now we have, and we can do that and impose the assumption for this revision country by country, especially in Europe. Back to you.
Thank you very much. So my question would be around, do you see constraints on, so we see that electrolysis and steam methane reforming will be we will have complementarity between both. And so do you see constraints for example, renewable electricity by potential by country, or from at the side, let's say, of steam methane reforming, carbon storage availability, carbon storage sites availability. And so taking into account these two types of constraints from both sides, will the gas exporting countries still be hydrogen exporting countries, or we would see maybe a switch in forces, taking into account also the demand and exactly the strategies that would be taken into account? Thank you.
Yeah, thank you so much. Yeah, thank you so much for this question. Yes, completely. We consider both of these, even the complementary of the blue and green hydrogen together, as I mentioned, even in terms of the technology, if we can apply in some part heat produced from renewables, so we may have reach more share of the carbon capturing, maybe by 99% or 100%. So this is in terms of the technology, and in other terms related to the potential that you correctly mentioned. Yes, in both cases we have limited potential. Even in green hydrogen, we see that, for example, maybe the renewable potential is not in for I just can say, for example, for the current amount of the hydrogen produced through gray hydrogen, if we want to decarbonize this current level of the production by green hydrogen, we need a potential of renewable amounting to the total for the Germany. So we see that even decarbonization of the current level is very huge in terms of that we want to all of these, if we want to reach all of this through the green hydrogen. So potential is limited, and especially if there is another thing, electrification. So the hydrogen is not the only solution for the carbon neutrality. We have electrification, and for that a lot of sectors need to be electrified in the future for the carbon neutrality. But so for that electrification, we need again electricity from the renewables. So not only the potential is limited, but also we need to reserve and secure some of those potential for the electrification, not only to the electrolyzers and for the green hydrogen. And on that side, on blue hydrogens, yes, exactly as you mentioned, there is limited potential for the capturing storage, for the carbon capturing and storage. So in this case, we see that, for example, some countries like in Middle East and some producing natural gas, like our members, that have natural gas to be used as feedstock for the hydrogen for the reforming. And also they have the mature and depleted fields for the carbon to be stored inside. So they have very huge potential to go for the blue hydrogen and export that hydrogen to Europe and other places. So in this case, we see a very huge potential for our countries, for gas exporting countries, to go through the hydrogen, especially blue hydrogen, and in some cases with coupling with renewable, to have a market in the future and becoming kind of the hydrogen exporting countries. Back to you.
Thank you very much for your complete answer. Thank you.
Thank you. Thank you.
Thank you very much. So now we go to our third presentation. So I give the floor to Lukas Saars.
Thank you very much. I think I need a minute to share my screen. I hope you all can see my screen now.
Perfect.
Yeah, sure. Thank you very much. My name is Lukas Saars. I'm working as research assistant at the University of Applied Science in Krefeld. It's a city in Germany. And I'm working at the Institute SWKE². So it's called SWKE², it's SWKE square. It's an institute for energy technology and energy management. And my main research interests include the investigation of different utilization pairs from electrolyzers from an economic and technical point of view. And now I'm very pleased to present my contribution today at this conference. The title of this presentation and of the contribution is Power to X modeling with identification of economic key factors using a bus fleet sensitivity analysis. And at the beginning, I would like to present the agenda for the lecture. First, I would like to start with a short introduction and describe the potentials of green hydrogen. Here the focus is particularly on the advantages of green hydrogen in heavy-duty mobility sector. Then in the second section, I would like to give a little insight into the use of hydrogen in public buses. I will then present the carbon dioxide emissions of various transport modes. So in the next section, I would like to present the case study with the main objectives of the study and the central assumptions we made in our case study. Then in the next section, I would like to present the methods in optimizing the size of the hydrogen storage from an economic point of view. There we formulated the problem as a mixed integer linear programming problem. Then in the section 5, I would like to present the results of the economic efficiency calculation. Taking into account the storage modeling. Here, the net present value method is applied and the main influencing factors are quantified with the help of a sensitivity analysis. Then finally, in the last section, we have a short conclusion. And we want to discuss the main developments and the main influencing factors. First, I want to start with the introduction. Here is a forecast. You can see a forecast for global hydrogen demand by sector. This chart from the International Energy Agencies shows the global demand for hydrogen in different sectors. And we can clearly see that the use of hydrogen in transport sector currently still plays a less important role. However, forecasts show that the hydrogen demand could grow to 66.5 megatons per year by 2050. And by 2070, demand in the transport sector could even rise to 158.2 megatons per year. So let's have a closer look at the hydrogen demand in transport sector. Here we can see the predicted rapid development, and it makes clear that hydrogen will play an important role in the transport sector in the future, and we already heard it in the second presentation. From near to zero in 2019 to 158 in 2070. Now I want to give a short overview of hydrogen in heavy-duty transport sector. As we already seen on the previous slide, hydrogen as fuel in the transport sector is seen as a promising application case. There are applications in mobility that are difficult to electrify. These are mostly the applications in which the use of hydrogen brings advantages. The applications include heavy-duty transport sector, which is characterized by little flexibility. And here we can see three of the most essential advantages of hydrogen in mobility. It's range, refueling time, and storability. And first, range. Potentially, longer ranges can be achieved with the use of hydrogen in the heavy-duty sector. And this at the same time, obviously, is one of the biggest criticism of electromobility. But at present, the market only offers public buses with longer ranges to a limited extent. Therefore, this advantages still needs to put into perspective, because often the fuel cell buses have similar ranges as electric buses. So the technological development needs to bring or to offer more fuel cell buses with longer ranges than electric buses, so that this advantage really is an advantage. Then to refueling time, depending on the pressure in the hydrogen storage tank, fuel cell buses can be refueled much faster than electric buses can be charged. But however, this argument can only be used if the range of the electric bus is not sufficient to make the bus cycles. Often the buses are parked in depot at night anyway and can be charged without any problems, because overnight there are long standing times and there's no problem with charging the buses. Then the last advantage is storability. Hydrogen can be stored much better than electrical energy. Supply and demand can therefore be better diverge in time, and this offers significantly more flexibility, and was and is one of the biggest advantages for the use of hydrogen. Now I would like to look specifically at the use of hydrogen in fuel cell buses. Here you can see the greenhouse gas emissions by transport mode. The graph on the left shows that in addition to cars, a large proportion of carbon dioxide emissions are caused by heavy-duty trucks. Here you can see heavy-duty trucks cause like 18.7% of global carbon dioxide emissions in the transport sector. And this fact kind of illustrates the reduction potential for carbon dioxide emissions in the heavy-duty sector. And on the right, I put another graph. It's carbon dioxide emissions by transport mode per person kilometer. So yeah, in particular, since public buses are rarely used to capacity, like we can see in the table below, utilization by transport mode. Here's a plane with 82%, and a public bus was assumed with 21%. So they have high specific greenhouse gas emissions, and this and the fact that the use of hydrogen in vehicles can have potential range advantages and shorter refueling times are increasingly bringing hydrogen production into the focus of local public for providers of local public transport. So here in Krefeld in Germany, there's one provider of local public transport, and they plan to use 10 fuel cell buses in their cycles, in their bus cycles. And so it's really a topic which is currently really interesting for the providers of transport in Germany. Now I would like to present the case study and the associated assumptions we made in the case study. I want to start with the overall objectives. First, we developed a tool for the economic evaluation of the bus fleet with the electrolyzer, with hydrogen filling station, with hydrogen storage and compressor. And we take into account the investments and the operation costs for all of these components. And here the net present value method was used in the tool. The assumptions on investments and other key figures can be changed variably in the tool to keep the tool dynamic. And second, the modeling of the hydrogen storage system, taking into account the favorable electricity prices on the stock exchange. At this point, the exchange electricity prices from 2019 were used to calculate the potential from favorable spot market prices. The potentials are increased by a larger hydrogen storage. However, this is associated with high investments, so that is an optimization problem. But we will take a look at this later on other slides. Then a third objective, sensitivity analysis with variation of the key factors. The sensitivity analysis quantifies the influence of the main parameters on the result of the profitability calculation. And we just want, with the sensitivity analysis in the fourth step, to identify and quantify the key factors with significant influence on the result of the economic efficiency calculation. Here are some central assumptions we made in our case study for the bus fleet. In the table of the top is are the fuel cell buses, and on the table below, the diesel-powered buses. The diesel-powered buses, we have to make assumptions because we take into account the diesel-powered buses as avoided costs, because when we use 10 fuel cell buses, we don't use anymore the diesel-powered buses. And for that, we make central assumptions like number of deployed FCBs is 10, and CapEx like 650,000 euros. But I think considering the limited time, I do not want to present all the assumptions. You can see it in the paper or in the contribution. So I think we can skip this slide. And if there are any questions, we come back to the slide later on. Then now I will present the modeling and the optimization of the hydrogen store. Here we can see the target function of the optimization and the modeling. But first of all, for the transferability of the results to all constellations of electrolyzer, we want to introduce the unit electrolyzer full-out hours. So it's just easier to make the optimization because we just take a look at full hours. For example, if an electrolyzer can produce 1 kilogram hydrogen per hour, the associated storage with an exemplary storage size of 10 kilograms hydrogen is equivalent to a storage size of 10 full-out hours. So it's just easier for the modeling. Yes, and the binary decision vector is noted as X, and C contains the hourly exchange electricity prices. So with the formulation of the objective function, the goal is to minimize the product of full-out hours and exchange electricity price. And in the second box, the decision vector X is shown. Here you can see the 3 days, for example, with potentially 24 hours to refuel the storage. So each day therefore has 24 hours in which the hydrogen storage can potentially be refueled. And the aim is that the most favorable hours are chosen through the optimization. So to determine the cost optimal electrolyzer operation mode, the optimal electricity price forecast is needed, because you just have to know the prices in the future to do kind of optimization we see on this slide. And finally, I want to say the model contains further constraints which are not presented due to the short time available, and can be read in the paper too. Now I want to show this graph. In the following, the hydrogen level is shown for an exemplary storage. So you can see the storage level in blue, the hydrogen storage level in blue, and in orange, the electricity prices. And the aim is to take advantage of the favorable electricity prices on the stock exchange with the help of the hydrogen storage system. And here in the graph, you can see that the storage tank is mostly refueled at very favorable prices. And in addition, the storage tank must be filled at certain times in order to be able to serve the regular demand of the hydrogen buses, because we assume in our model that the 10 fuel cell buses have a regular demand for the hydrogen and have to be refueled every day. So it is possible that not every favorable price can be used in our model because we have a regular demand. Now I want to give a quick overview of the design for the hydrogen storage. Here I already talk about the electrolyzer full-out hours. we can see the graph shows the optimization potential in form of favorable exchange electricity prices for different scenarios. So we can see a hydrogen demand from of 12 full-load hours and until to 24 full-load hours. And when I have 12 full-load hours, there are free capacities in the hydrogen store to just use the capacities to refuel the storage when the electricity price is really cheap. So the lower the hydrogen demand, the greater the free capacities. So the favorable prices can be selected. And the graph clearly shows that the storage should not be designed to be infinitely large, since the optimization potential decreases significantly above a certain size. Here you can see that the potential of the optimization of the decreasing the electricity price is above a certain size, the potential decreases significantly. The economic optimization potential due to larger design of the hydrogen storage tank is very low. Therefore, the storage is designed to be small in our tool, in our case study. Our assumption is 780 kilograms with a 1 megawatt electrolyzer. So to the short abstract, bigger storage or electrolyzer, higher optimization potential. However, potential exhausted above a certain size, and these results are considered in the business case and the case study. Now we will take a look at the results of the profitability calculation. This includes, in particular, the result for the net present value and the levelized cost of energy for the hydrogen. So here we can see the levelized cost of energy for the hydrogen, and the graph shows that the exchange electricity price and the ancillary electricity cost or other electricity price components have a significant influence on the result of the profitability analysis. So we can see levelized cost of energy in our case study, 5.99 euros per kilogram, and the residual value with minus 0.40 euro per kilogram. And here you can see the results, including the residual values, the levelized cost of energy with the residual values 5.60 euros per kilogram, and the carbon dioxide savings 603 tons per year in comparison with conventional diesel buses, 10 diesel buses. And the net present value is minus 6.7 million euros in a period under review of 20 years. Now I want to show the sensitivity analysis. For the analysis, we have varied the values for the main influencing factors upwards and downwards and investigated what impact this has on the net present value. Here you can see the key factors, the diesel price, the hydrogen demand per kilometer, the exchange electricity price, and price for carbon dioxide emissions. And we have a base case in the middle and our varied values. And we can see our base case net present value, as we already seen on the slide before, of minus 6.7 million euro. This graph illustrates that the assumed hydrogen demand of 10 kilograms per 100 kilometers from the fuel cell buses has a very significant influence on the result. And however, the price of carbon dioxide emissions has only a very small influence on the result. The price for carbon dioxide emissions would therefore have to be increased significantly to see a positive effect for the net present value. And now we add a levy to the electricity price of 67.56 euros per megawatt hour. The levy corresponds to the renewable energy levy in Germany and comes from the renewable energy law in Germany. And we can clearly see that the levy has a significant impact on the result and reduces the net present value by 1.9 billion euros. And the next step, we add a tax on the electricity price with 20.5 euros per megawatt hour. The next, and here we have chosen 20.5 euros per megawatt hour, as this corresponds to the electricity tax in Germany. And here too, we can see that the sensitivity analysis shows the significant impact of the electricity tax on the result of the profitability calculation, and reduces the net present value by further 560,000 euros. So the electricity price has a significant influence on the results of the economic calculation. So before we add the levy and the tax, the net present value was minus 6.7 million euros. Then with the levy and the tax, we have we have reduced the net present value by 2.47 million euros, and we get a net present value of minus 9.8 million euros. Now I want to give a short conclusion. The studies show that there are two very important factors: the electricity cost and funding programs, funding rates, which are different in countries, which have a significant influence on the result of the economic efficiency calculation. And in particular, the results and outcomes from the national hydrogen strategies and the roadmaps of the individual federal states will significantly influence the dynamics of the expansion of electrolysis capacity. There's a great potential for achieving high efficiencies, which is attributed to high temperature electrolyzers. It's called SOEC electrolyzer. Potentially efficiencies up to 80%. And the combination of utilization path for the products hydrogen, oxygen, and heat offers great potential for optimizing the economic efficiency of water electrolyzers and taking into account the site-specific parameters. So thank you very much for your attention, and feel free to ask questions and make comments. Thank you.
Thank you very much. So do we have some raised hands?
I don't see any raised hands. Somebody has a question. Please.
All right, so my question is regarding the residual value that you present. What do you put behind that? Is it like some the value of the bus fleet somehow, or do you take into account maybe some flexibility provision by the electrolyzers? Or
we consider it 10 fuel cell buses and a hydrogen filling station and a hydrogen storage tank. So they all have high investments, and we take into account as avoided costs 10 diesel buses, because we don't have to use the diesel buses when we operate fuel cell buses. And the fuel cell buses have other operation costs than the diesel buses, and we took into account all of these aspects.
okay, thank you very much. And so my second question is regarding the sensitivity analysis. You've tested different variations on different components of the system. Did you also test the variation if the capex of the electrolyzer varies, or is it constant throughout the whole time frame?
That is a constant in our model, but because we do literature research and try to do mean variables of all these literature, so it was difficult to find values and assumptions for the investment for the electrolyzers. So we had it constant in our model, but I think it makes sense to variable the capex of the electrolyzer too.
Yeah, thank you very much. It was a very interesting presentation, and I think with the 3 presentations, we've tackled the different aspects of this the hydrogen topic. So I don't know if there are still other questions from the audience. And otherwise, maybe we can close the session. Session host.
No, I was waiting for some hands to be raised, but I don't see any. So yeah, no further questions.
Okay, so thank you very much, everyone, and good luck with your research. It's a very hot topic, and we might maybe meet in other sessions. Thank you. Have a nice day.
Thank you all, and thanks to the organization.
Thank you very much.
Thank you. Have a nice day.
You too. Bye.
Thank you.
Bye.
Thank you. Bye.